Let us derive the expression for the force on conductor in an electrostatic system. So we know how to find the force because of point charges and all those. However, let us say that we have a system of conductors with some potential or some charges in an electrostatic field situation or system. Now we want to find the force on these conductors. How to do that? So what we will do, we will use principle of virtual displacement. As you know that force does a work which is given by this. So we can have an idea that the magnitude of force will be given by this thing. So we will use this principle. Means we are not going to actually move any conductor. We are just thinking that what will happen when we move a conductor by some virtual displacement dl. Then we will find the force because of this using this scenario. So now in case of conductors in electrostatic system, there can be two situations. First one, when we assume that the charges on the conductors is constant. The other scenario will be voltage constant on the conductors. So first we will take when charges are constant. Charges are constant means these conductors are isolated. Means there is nothing externally supplying charge. So let us say I move this one plate by some displacement dl. So the work done by the system will be equal to force when charges are constant dot dl. Now since nothing is providing anything from outside, so this dw is actually going to reduce the stored energy because system is doing work from its own stored energy. Now you might remember from my lecture on gradient that dw is simply written as delta we dot dl. It implies delta we dot dl is equal to minus fq dot dl. So on comparing these two, we can see that the force when charges are constant is simply minus of delta we, that is minus of gradient of the stored potential energy. Now let us see what happens when the conductor voltages are constant. It means when voltages are constant, it means that we are connecting some source to them to keep their voltage constant, and these sources are going to supply some charge whenever required so that potentials are kept constant. So what will happen? So the work done by the or energy supplied by the source will be equal to the charge supplied into the voltage of the conductors. Okay. However, we know that the electrical energy is simply given as electrostatic potential energy is given as half of dqk bk. Now work done by the system due to virtual displacement will be the force into displacement. This V subscript shows that we are considering the force when the voltages are constant. Now on comparing these two, we see that dws is equal to twice of dwe. Okay. Now by principle of conservation of energy, we see that the work done by the source should be equal to the energy stored plus the energy consumed due to the displacement. So we see that dws is equal to dws by 2 plus dw. It implies dw is equal to dws by 2. Now dws by 2 is simply again dwe only. So you see dw, which is simply equal to fv dot dl, is now equal to simply dwe, which is delta we dot dl. So on comparing these two, we can see that force when the voltage are kept constant is simply delta we. So you might be wondering by comparing these two equations that when the charges are kept constant, we have this equation minus delta we. When voltages are kept constant, then we have this equation delta we. So is the force going to have opposite direction? Practically, the force will have same direction. Either we use this equation or this equation. Both equation will give the same direction of force, because for a given system of conductors and potentials, the voltage neither depends on how much displacement we are giving. This force does not depend neither on the displacement which we are giving, nor on the change in charge or voltage which we are going to do. It depends on the configuration already which is present in the system, that is already the charge and the potential which are there. So it doesn't matter whether we are going to keep charge constant or voltage constant, or how much displacement we are giving, the force should be same, although superficially it appears that the force direction will be different or opposite in these two equations. So let us verify this. Let us take a parallel plate capacitor with voltage V, and this displacement is, let us say, x. So we know C is equal to A epsilon naught over x. Now we know that force when charge is kept constant is minus delta WE. Now delta WE, we know that half CV square. Now since charge is constant, so we will replace V by Q by C so that we can keep charge constant. So half C Q square by C square. So it will be Q square by 2C. Now we are assuming that displacement is only in x direction. So delta WE is simply dou WE by dou x. So it implies minus delta WE is simply minus dou by dou x of delta WE, which is Q square by 2C, or minus Q square by 2 dou by dou x of 1 by C is equal to minus Q square by 2 and dou by dou x of 1 by C. 1 by C is x by A epsilon naught. So it is minus Q square by 2 A epsilon naught. So this is the force when charges are kept constant. Remember this. Now let us take a scenario when voltages are kept constant. Sorry. So force when voltages are kept constant is delta WE. So delta W is simply dou by dou x of WE is equal to dou by dou x of half CV square. Since voltages are kept constant, so we can bring it outside, dou by dou x of C A epsilon naught by x. So it is half V square A epsilon naught minus 1 by x square. So it is minus 1 by 2 V square into A epsilon naught by x into 1 by x. So it is minus 1 by 2 V into x into A epsilon naught x into V. So this is CV. So it is equal to minus 1 by 2 QV by x. Now we have to compare these two. This is FV, and FQ was minus Q square by 2A epsilon naught. Now we have to show that these both are equal. How to do that? That is minus QV by 2x actually equal to minus Q square by 2A epsilon naught. Let us do that. V is equal to Q by C. So I will put this minus Q into Q by C. C is A epsilon naught over x. So clearly this is equal to minus Q by 2A epsilon naught. Both are equal. So you see that both formula are giving the same force and direction is also same. Now there is one more point to note, that you see that this force is negative, means it is trying to oppose the increase in x. Means if I try to increase x, the force will oppose it. So it means the force is attractive in nature. So this we can see. So you see that the electrostatic force is now attracting in nature. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group whose link is given in the description of this video. Thank you.